started with the Lagrangian that write as a kinetic term plus a potential, which actually had the wrong sign for the mass, and like so. That was our Lagrangian. And again, this is the wrong sign, wrong mass sign. And so again, because of this wrong sign right here, you basically get a potential that then looks like this, right? It's like a sort of, yeah, so two-dimensional. And there's this gutter that goes around it. So it's like the bottom of a sombrero hat or a wine bottle. And this point right, or this entire ring around here, basically is a minimum that's specified by phi star phi, which is the magnitude of phi squared, which is then basically m squared over 2 lambda, which then we define, we call A to make things easy. Okay. Then we said, well, we need to shift things. So this right here is actually expanded about this point, right? And that's no good. So what we want to do is you want to shift to the new vacuum state, which is actually here. And you can do that actually, well, so I did it in 2 ways. One, I used polar coordinates, right? And then at the end, I said, well, you can also do this in Cartesian coordinates. You can also write phi is equal to that A, the expectation value, plus basically phi1 plus I phi 2 over the square root of 2, right? And if you take this and you stick it in here, what that does is it transforms the Lagrange density rather, to 2 real scalar fields. And like so. Okay, so again, start with this Lagrange density with the wrong mass sign. Then we notice that actually it has a minimum here. There's still a maximum. There's another sort of stationary point here, but that's a maximum. Then what you do is you say, well, we have to expand around this new vacuum right here, which you do by making this shift. You take this and you stick it in here, you expand it out. And then again, the miracle that happens, right, is that now this thing, the phi1 field has a mass, right, but it's the proper sign. So this actually has the correct sign, but phi2 doesn't have a mass. So basically phi2 is the Goldstone boson, okay? So that was what we did last time. Now, what I'm gonna argue is that basically, in any theory like this, so with more scalar fields, more complicated scalar fields, what you want to understand is how many Goldstone bosons actually emerge from your calculations. So in this case, there's only one Goldstone boson, and that's the phi2 field, right? It's the phi2 field that's the Goldstone boson. And so, but later on, I'm going to argue that it's the group theory that basically determines the number of Goldstone bosons. And basically, okay, what we're going to do is going to say, okay, let's say we start with some group G, which has dimension D, okay? And we break it down to a subgroup H, which has dimension, let's say E, okay? Then the number of Goldstone bosons is going to be the number of generators in the coset space. All right. So let me see. So the number of Goldstone bosons, is going to be equal to this dimension minus. Is that right? Yeah. Hold on. Let me. Because that's the grand conclusion of all this. So let me make sure. Group, subgroup, So, okay, yeah, the number, okay, so the number of massive, okay, the number of massive bosons is actually going to be equal to the dimension of H, right? And the number of Goldstone bosons is actually going to be the original dimension minus the number of massive things. So, okay, so if you take massive boson, that also doesn't feel quite right. Oh, no, hold on. One Boson bosons is the original dimension minus okay. All right. Well, so we got one Boson boson in this case. Okay. Yeah. So this is correct. This is not correct, but this is actually correct. And actually, we don't care how many massive bosons there are. We just care about the number of Goldstone bosons. Okay. So let's take a look at this particular example. What was the symmetry that we had? So the symmetry was that we basically can take this field and we can change it by a phase, like so. And actually, nothing changes in this Lagrange density. And actually, therefore, nothing changes in the equations of motion. All right. So the original group that we had in this case was U1 or SO2, basically rotations in a plane. And that has one dimension. So basically, that has one dimension like so, okay? What do we break it down to? Well, we break it down to nothing, right? There's no symmetry left at the end of this. And so basically, there's no subgroup. So basically, the dimension of the subgroup that we broke it down to, which is nothing, is 0. So the number of Goldstone bosons is actually 1, which is actually correct, okay? So this example is a little bit, it doesn't show how you generalize Goldstone's theorem to like higher theories. And so that's what I'm going to do next. So I wanted to remind you of this and sort of give you a preview of what's coming, right? And what we want to do is figure out the number of Goldstone bosons. And here you can kind of trivially see that what I've written down is correct. I haven't derived this at all. I'm just telling you. But what I'm going to do is I'm going to do another example, which is more less trivial, and then basically come back and hit the same thing. Okay. But the important point is all the stuff about like counting number of Goldstone bosons is already embedded in this. Okay. So now, with that sort of awkward introduction, let me move on to a more complicated theory. All right. Let me try, let me see. I'm going to try the blue pen because, all right. So now the new Lagrange density we're considering. Okay, so can you guys see that? Is that okay? Is that dark enough? Good. All right. So we're going to consider a theory that's invariant under SO3. Yeah, Nathan, if you want to close it, go ahead. So basically, these are rotations. It's a non-abelian group. So this is rotations in three-dimensional space. What we mean by non-abelian is that basically two group transformations don't necessarily commute with one another. And so there's a nice example of that, right? So if you do rotations in a plane, right? If you rotate the book in a plane, it doesn't matter whether you go 10 degrees or 20 degrees or 20 degrees and 10 degrees, you're going to end up in the same place. But if you do rotations in three-dimensional space, it very much does matter how you do the rotation. So I'm going to rotate around this axis and then this axis. These are two axes I'm going to rotate around. And I'm going to do by 90 degrees, but I'm going to do them in a different order. So basically, first I'm going to do this, and then this. Remember how I wrote, hold on. So I'm going to go, let me use the right-handed rotation. So I'm going to do this and this, right? Versus this and this. So two rotations. Basically, I'm rotating around the same axes, but I'm just doing it in different orders. So the point is, in that case, the transformations do not commute. So that's a non-commutative algebra, and it's basically a non-abelian group, right? And that's sort of the hallmark of non-abelian. Okay, so this is rotations in three-dimensional space, but be careful, this isn't real space. This is the abstract space of the fields, okay? So that's actually very important. All right, so how do we write this? So we write 1/2, like so, and like so. So the first thing you notice is there are three fields. So basically I goes 1, 2, 3, like that, okay? And now notice that basically we have the same, where you have the 1/2 versus this. But again, remember, this is a complex field. This is now a real field. And we could actually transform this into this by that Cartesian representation that I gave before, okay? So then again, we're going to take the wrong sign for the mass because we want symmetry breaking. And we're also going to have the quartic term, which is like this, okay? So, this Lagrangian is invariant under this three-dimensional rotation, okay? The thing is, basically here, all of these things are quadratic, right? So in some sense, these, the phi is similar to something like r squared, the magnitude of some unit vector. And in real three-dimensional space, you guys are familiar, doesn't matter how you rotate stuff, the distance squared is an invariant, okay? So the same thing is true here, but again, this is an internal space. This is not physical space. This is not coordinate space. Okay, so that's something that's a little bit hard maybe to get around. And actually, this generalizes. You can consider higher groups here, right? And then in the higher groups, right, the index can go 1 to n depending on what kind of group you're talking about. So you can talk about SON, right, which is orthogonal rotations in an n-dimensional space, and then basically there's a group like that, and it's just it's more complicated than this, but the idea is the same. Okay, now what does this thing look like under a group transformation? So this is hopefully you've seen some of this before, but the idea is under this SO3 transformation, or in the back of your mind, you can say, well, this generalizes when I goes 1 to n, and for other non-abelian groups, this is going to transform like e to the minus I, tk, alpha k, and then ij, and phi j, right? And then we can write this as some matrix like this. All right. All the indices in the specific, so it's probably best to keep the specific example in mind, but again, remember it's easily generalizable. But here I'm talking about the indices running 1 to 3. So all these indices run 1 to 3, and this is a 3 by 3 matrix. So again, this is based on SO3. So it's not real configuration. It's not physical coordinate space. But if you want to keep something in the back of your mind, if this were coordinate space, this would be basically the 3 by 3 rotation matrices in general. So that's all it is. Now, this is actually a way of representing those rotations. So basically, this means this right here. Okay, and these are basically the parameters. So again, I write it as alpha sub k, but basically these would be angles. If we were talking about real space, there would be like 3 different angles, rotations in 3 different directions. These are the generators of the group. And this is basically the heart of how you generate algebras, right? Or non-abelian symmetries. is you need to figure out what the generators are. And these indices actually go with these. So this is a 3x3 matrix. This is a 3x3 matrix right here, okay? So then the first thing, so what TK means, it is actually the kth generator, and then basically I and J run 1, 2, 3, okay? And basically the generators have to have the same dimension, obviously, as this. So again, if this is a 3x3 matrix, right, then you do this exponential expansion, and then you get a 3x3 matrix, and then that multiplies a 1x3 vector in this abstract space, and then that provides the transformation from one to the other. Okay. Now, so have you guys seen this before? Wait. So some yes, some no. All right. So if not, this is why. Yeah, Dan.
I was just gonna say I've seen it before.
What now?
I've seen it before.
Oh, you've seen it before? Okay. All right. Good. So also, if you take second semester of E&M graduate level, this basically this is done for the Lorentz group. So Patrick, so I know you've seen it because basically we did the Lorentz group, right? So that this is basically that. Okay. Okay. So let's do some specifics then. So in this abstract rotation space, let's write down what the TKs are. Okay, and I'm going to be a little bit sloppy with where the indices are. Actually, since we're not going to do space-time stuff, I don't think it matters too much. So yeah, the generators, and then basically I'm going to label them like this. So they're matrices, and these are basically the angular momentum generators. So it's Jij1, Jij2, Jij3. And one is like X, so it's like generators of the X rotations. This is like Y, and this is Z, okay? So if you want to know specifically what these look like, a particular representation is the following. And I'll write this small. So J3, which is JZ, is actually equal to 0 minus I, 0, 0, 0, 0, 0, 0. So it's that, okay? And then J1, which is JZ, J1, which is JX, is basically 0, 0, 0, 0, 0, minus I, 0, 0, like that. And then finally, J2 is JY, which is basically 0, 0, I, 0, 0, 0, minus I, 0, 0, like that. So these are the generators for rotations. And if you take a look at this, right, if I put the JKs in here and I have like an alpha 1, alpha 2, alpha 3, basically you can construct a matrix that's basically has, that on the diagonal is zeros, but basically is any arbitrary thing that's anti-symmetric in the off diagonal thing. So you can, by picking different alphas and dotting them with this, and notice what I'm dotting is the K index, not the I and J index. The I and J index go with this, not with that, right? I can basically generate a general rotation matrix in this way. Okay. All right. Another thing. So actually, so this is a long lead-in to eventually get to symmetry breaking. So this actually is essentially quick and dirty group theory. All right. All right. So now another thing about these generators is they satisfy the following algebra. So basically, if you take JX and then JY minus JY, JX, that equals I, JZ, and plus cyclic permutations of the following. And what I mean by cyclic the Z, I guess, since I'm going upstairs, I should keep it up. So cyclic permutations just means you push the X, Y, and Z through. So you put the X here, and then the Y and Z come here, and then you push that through, and then you get the other. So there's basically three of these sort of anti-commuting relationships for the generators, okay? And you can draw a direct line from this, the fact that these don't commute, the generators don't commute, to that thing that I did with the rotations. The fact that rotations don't commute in general is basically tied to this. Notice that's different from this. Here, it was just numbers, right? The generators were just simple numbers. And for numbers, right, I can take lambda 1 and commute with lambda 2, and that's 0. Okay? So because it doesn't, for just numbers, it doesn't matter if I take lambda 1 times lambda 2 or lambda 2 times lambda 1, I get the same thing. So I take the commutator of that, then I get 0. So for this abelian group, right, basically the rotations do commute, and that's tied with the fact that this is commuting for SO3 or higher non-abelian groups. You have relationships of the generators that go like this, and that's tied with the fact that transformations done in different order don't commute with one another. Okay? And so anyway, this forms the algebra of the group. Now, let me ask you guys something. Have you seen this before? This. Have you guys seen this before?
You see that in quantum, right?
Yeah, it's basically just the algebra for angular momentum. So basically, let me write up here. So you guys are all familiar with basically Li Lj is equal to I H bar epsilon ijk Lk. And so I've introduced the epsilon ijk symbol, but basically that's the standard commutation relationships for angular momentum operators in quantum mechanics that you learn even in quantum 1. Okay.
Is J still the combination of angular momentum and intrinsic spin?
Here, no, I'm not doing spin yet. Yeah, this isn't with because again, this is SO3, right? To get spin, I need to do SO2, SU2, right? Okay. So let me. Well, actually, so if you want, I can skip ahead. I have an example that I have an example here where I show how this, with this background here, actually is a rotation. Do you guys want to see that, or you want me to move on? Move on? Or proceed? Okay. So, I mean, Patrick, Dan?
I'd be fine if you went through it.
Okay, all right. So what I'm going to do, so I'm going to do an example here. Oh, I guess the other thing I should say is this Lagrange density is invariant under that transformation that I just erased. So if you do that transformation and you stick it in here, because I have squares like this, the Lagrange density is invariant under that transformation, right? Just the same way this was invariant under this. But again, as we're going to see, because I have the wrong sign here, right, it's going to develop a non-zero vacuum expectation value, and that the location of that vacuum expectation value is going to break the symmetry. So the ground state or the vacuum state breaks the symmetry, even though the Lagrange density basically is invariant under, say, this for this Lagrange density, or this for the thing that I just erased here. Okay. So let's do. So this is my example. All right. So it's I, and then basically J, Z, and theta. Okay. So based on what I said, basically this should be a rotation around the z-axis by an angle theta. That's what this should be. Okay. This is the generators of rotation in z. That's some angle. And so that's going to lead to the transformation, or should lead to the transformation of rotation about the z-axis. All right. So let's expand this. So actually, the first thing is that when we expand it, the first term in the exponential is just the unit vector, 1. But it's actually not it's not the unit. It's not 1, but it's the 3 by 3 unit matrix. All right, because that's right. The first term in the expansion of the exponential is 1, but again, we got matrices up here. So the first term is actually be a 3 by 3 unit matrix, which is this. So 3 by 3. Okay. Then the next term is basically this I, J, Z, theta. Okay. And then the next term is minus J, Z squared, theta squared over 2 factorial. And then the next one is minus I, J, Z cubed, theta cubed over 3 factorial. Okay. So you guys will recognize the standard expansion. And again, but notice the JZs are those 3 by 3 matrices that I've written over there. Okay. So the JZs are basically this. And so you can see why this becomes interesting to calculate, because this isn't just a number that you're squaring. You got to do matrix multiplication. Okay, so you take 2 matrices, it's 3 by 3. It only has 2 elements, so it's probably not too bad. But you can quickly see, right, that you're going to have to keep multiplying these 3 by 3 matrices. Fortunately, there is a pattern. So if you do this, the first thing is going to give you 1, 1, 1, and then zeros. Okay, so I'm going to these zeros here are zeros for everything on the off diagonal. Okay. Now the next term is basically theta times 0, 1, 0, minus 1, 0, 0, 0, 0, 0. Okay. So it's basically just JZ, which is there, multiplied by I, and then like that. Okay. The next term is basically theta squared over 2 factorial. Now, okay, you can do the JZ squared. It's fairly straightforward. And what you get is you get minus 1, 0, and then zeros in the off diagonal. Okay, so it's not a unit matrix. It's not even a negative of the unit matrix because it's got a 0 here. But it is a diagonal matrix with the 2 non-zero things being here, which of course makes sense because if you multiply these by each other, this isn't going to play any role. So it's just going to be up here in this submatrix that you get. And what you get is actually that. And then the final thing, you get plus theta cubed over 3 factorial. And then you get 0, minus 1, plus 1, 0, 0, 0, 0, 0, 0. Okay. So at this point, you can kind of see how the pattern is going to go. The first thing is a unit matrix, but then the first odd term is sort of this off diagonal matrix with a 1 and minus 1. Then the next odd term is again off diagonal with now minus 1 and 1, right? And then we have basically these even terms. The next even term is going to be something similar to this, except it's going to be pluses, and it's going to be theta to the 4 factorial. Okay, so if you put this all together, what you find is you get a cosine theta up here. Why? Well, you get a 1. You get no odd term, which is good because it's cosine expansion. Then the next term is actually minus theta squared over 2 factorial. That's the next term in the cosine expansion. Then you don't get anything here, and then you go on. Okay. And then also, if you look, this term right here, if you go all the way through, you'll get a cosine theta expansion here, right? Then in this last row and last column, the only thing that you get is the 1 that comes from here. And then you get 0, 0, 0, 0 here. Okay. What about the even terms? So for the even terms, we've got, well, first of all, we're going to get opposite signs here, right? The first even term here is theta. Oh, sorry, the next odd term. So we did the even terms. Now we're counting the odd terms. So the odd term, first odd term is theta. The next odd term is minus theta cubed over 3 factorial. And you can kind of see that's the beginning of the sine theta expansion. So basically, this is sine theta. Okay. Then let's do the same thing for the next odd terms. But now we start with negative. And now here also the sign switches. Okay. And so if you look at what that expansion is, it's actually minus sine theta. And there you go. So that's the big result of all this. By doing this with those matrices, what you end up with is basically a rotation matrix around the z-axis, because notice you keep the z-axis the same. You're only rotating x and y. So this is a way of generating rotations around the z-axis. And actually, in general, if this is, all the j's dotted with 3 different angles, that's a way of representing general rotations in 3-dimensional space. Okay? All right. So any questions? Let me take a drink of coffee, look over the next part of my notes.
Would you be able to offer just a little bit of physical interpretation about what the rotation is accomplishing, since you said it's not in space, in coordinate space?
Yeah, so it's everything is by analogy. So this is an abstract internal space that you're rotating in. So you're rotating in some kind of field space. So the first sort of, I don't know if it's the first, but the one of the first sort of examples of this was isospin. Okay, so what isospin was Heisenberg noticed that basically if you look at the proton neutron and you ignore the slight mass difference, they're basically similar particles which he called nucleons, and there's certain like invariants of nuclear interactions that you can get by rotating them into each other, like by swapping them or rotating them in some fashion. And so that led to isospin, and that actually was an SU2 symmetry, right? And the reason it was called isospin, it stands for isotopic spin, because depending on the number of protons and neutrons in your nucleus, that determines the isotope, right? And so people already knew spin, and they already knew the algebra for spin. And then Pauli said, well, the proton and neutron are just like spin states. You have spin up, spin down, then you have proton neutron, right? But there's no up and down. Like that spin actually points up or down in physical space, but basically protons and neutrons, there's no physical space they point up into. And that was Heisenberg's thing. He was a very mathematical type. And so he said, well, just by analogy, the math works out the same, or I can apply the math there, right? And then basically Yang and Mills and others then go like, well, we can, instead of just SU2, we can play with other groups, right? And so back in the 60s and 70s, there was this flourishing of, grand unified theories, which sought to incorporate ever larger groups like SU5 that would encompass all the internal symmetries of the particles that people saw, okay? It turns out SU5 doesn't appear, at least in its simplest guise, to be a good way to grand unify all the forces. Okay. So, all right, I'm going to erase my example, unless you guys have questions. All right, so let's go back and take a look at the potential again. Okay, so again, this is my potential right here. And actually this right here is minus my potential. And this is a function of, I could write this either as a function of phi I or phi I squared, but actually more properly, it is actually a function of phi I squared like that. Okay, so if you take a look at this, we want to see where's the minimum. So how do we do that? We'd say like this, and that's minus m squared v sub I plus 4 lambda v sub I like that, and that's equal to 0. So you take the derivative of this, right, right here. Again, remember, this is minus b, so when I'm taking the derivative of b, that's what the minus sign is doing here. It's me bringing the minus sign here, and that's why this is a plus sign. Okay?
That 4 shouldn't be a 2, because phi is already a square term. So if you use the power 4, it gets like an 8 power.
Well, so really what you're doing here, you're multiplying each one of these. There's 4 of them, right? You're multiplying each in turn.
But the power, are you sure it is 4?
Yeah, it's 4.
So then the derivative would have a phi cube.
No, so basically there are 4 powers here, right? And so, I mean, in in a sloppy way, you could write this as e to the 4th, right? And then if you,
Yes, that's exactly what it was.
And then you say this, and
You
this is-
already have a phi square over there.
yeah, and this is basically, this is squared, so this is basically like, you know, like
So
m.
in other words, it's almost like you have 5 to the 8th.
Yeah, I'm afraid that
It's
should
like a
be a
5
power
times
of
5 all to the 4.
Because
It's like a
so
5
5
to
to
the 8.
the 4 is okay, but then you already have phi I, which sounds like a square. If you do another 4, you
Oh, you know, one thing I probably need to, I can't, the indices aren't right, actually. The indices aren't right. So you still,
Dimensionally though, like if you
I
were to
would
give, if you were to give 5 dimensions, that term would be of dimensions 8 power.
Sorry, yeah, you're right, actually. Okay, never mind, sorry, you are right. So the thing is, like, I get so used to working with one scalar field, it's, okay, lambda phi to the 4th, lambda phi to the 4th. Yeah, you're, okay, I got it now, I got it.
And
That's.
And now those two terms only differ by their prefactor, one with lambda and one with m squared over 2. That's the
Exactly.
only distinction.
Yeah, that's it. Well, yeah, they differ by the prefactor,
Oh,
but
but
notice
they're higher order.
lambda
Okay.
and this have they have different dimensions.
Yeah.
This is actually a coupling constant. This is a mass term, right? Yeah, you're right. Yeah. Okay. So you get so used to just writing phi to the 4th that. Okay, good call. But yeah, so now you agree, right?
Yeah.
Okay, all right. Anyway, so then you look for where does that equal 0? Well, there's one easy choice, right? That's phi is equal to 0, right? That's the unstable one. Now the thing is here, because of the dimensionality of this, the way that you would draw this is the following way. So it's actually a sphere like this. I'm trying to draw a sphere, and then basically you can think about moving around on the surfaces. So what's going to happen is this is a little bit hard to draw. So here I'm trying to indicate this is all the phis being 0 at this point, right? The center of the sphere is all the phis being 0, and then basically after the symmetry breaking. So actually I haven't written down the non-zero or the vacuum expectation value. Basically, the stable point shifts to there, okay? Stable point shifts to there, and then basically you can do rotations on this sphere. And actually there are 2 rotations that, that'll move you around the sphere, and then one that would actually move you off in, say, that direction, right? All right, anyway, so what's the other minimum that occurs? Well, so the other minimum is like, okay, well, if this isn't 0, then you can divide that out, and then you can basically say ji, which is basically, we're going to call it phi naught squared, is going to be equal to m squared over 4 lambda, or the magnitude of the vacuum expectation value is going to be the square root of m squared over 4 lambda, okay? So again, this is all the fields at 0, and basically this is shifting to that new vacuum point, right? This is shifting to the new minimum, like so. And now, but basically any point on the surface of the sphere is good, right? Any point is a minimum. So you have to choose one to take as the minimum, and basically that's the symmetry breaking. So let's choose one, and let's choose the vacuum to be broken in the 3rd direction, in this internal field space. So basically here's the symmetry breaking. We're going to say phi0 is equal to this magnitude m squared 4 lambda, and then basically in the 3rd direction, okay? So now, like if I have my axes 1, 2, and 3, what I'm doing is, I'm shifting my vacuum to be along in the 3 direction. Okay, so that's what this means. I mean, there are a multitude of ways you could do this. You could actually say, okay, I'm gonna go, you know, 1. I'm gonna go 1 and 2 over the square root of 2, right? That's a unit vector. Wait, hold on a second. Yeah, that's a unit vector. And so that's a unit vector, and then I multiply that by the magnitude like this, right? That would just be moving the back. That would be saying, okay, well, I'm going to choose this point over here to be my vacuum, right? It's arbitrary. That's the point. You have to break the symmetry somehow. The simplest thing to do is like say, okay, well, I know what my magnitude has to be, and then I need to just pick a direction, and that's the direction I pick, and that breaks the symmetry, right? Because this obviously is not in general invariant under those previous transformations that I made, right? This choice right here isn't. If I rotate around the 2 axis, let's say I rotate around the 2 axis, well, what that's going to do, it's going to move that vector to a different place. It's going to change, right? If I rotate around the 1 axis, it's also going to change the direction, right? There is still one remaining symmetry, right? And this is different from the previous case. In the previous case, we had a symmetry, this U1 symmetry, which we broke down to nothing. There was no remaining symmetry. But here, there is a remaining symmetry. If you rotate around that direction, then the vacuum still remains invariant. So there is a remaining symmetry. And in fact, that rotation around a single axis, that is in fact the SO2. That's rotations in a plane again. Okay, so in this case, we have a symmetry that's left over, and that's actually crucial in all of this. Okay.
Is that analogous to choosing a gauge but having some residual gauge freedom remaining?
No. So this is different than that, right? So we haven't talked about any gauge stuff. So that's a good point. Like eventually in the third lecture, I thought I was going to finish in 2, but like okay. The idea of gauging is that basically you let this be that this is a constant, right? And actually the other sort of transformations that I wrote down, more general ones, the e to the I tk alpha k and then ijk like that. Wait, repeat your question again. So now.
Oh, I asked, is the idea of the remaining symmetry even, is it related to the idea of gauge freedom remaining even after you choose a gauge?
Right, no. Okay, I don't think so, because basically to introduce gauge symmetry, which is again the third lecture in this, if you guys still want to come, is basically what you do is you allow this to be space-time dependent, right? And then you have to introduce a gauge field and so forth and so on. And then basically the equivalent thing that happens here is you let this, this alpha sub k, we're taking it to be they're just constants. There are 3 different constants, but just constants. But then the next step would be what Yang and Mills did. And they're like, what? Hey, why don't we just let this guy be space-time dependent? Let's see what happens. You can do that. Some things change in the Lagrangian then, but then you can basically restore the symmetry at a local level, right, by introducing gauge fields, right? So, but that's what I had in mind for the third lecture in the series. Okay. All right. So, all right. So again, let me just say this right here, still invariant under e to the minus I T3 alpha 3. So if I take my vacuum and I do this to it, right? So I take this vacuum and I rotate it about the third axis, then basically I still get the same thing back again, right? So there, anyway, the point is, now, if this is T1 or T2, then I have an inequality here, right? Because basically, if I rotate around different axes, then I'm going to rotate away from that point. But if I rotate around that axis, then basically my vacuum still remains invariant. So the point is, there's a larger symmetry that we start with. We do the symmetry breaking, right? And then basically at the end of the day, what happens is we do have a residual symmetry left over, which is basically rotations around this. Okay. So now let's do the work of basically shifting. So we know our vacuum expectation value, and now we're going to basically take this Lagrange density and we're going to shift it to the new vacuum. So this is expanded around here. What we need to do is we need to redefine our fields so that we shift our new vacuum to this point. That's what we're doing. So which is exactly the same thing that we did in the previous case, right? So what we're going to do is we're going to take our field in the third direction, because again, we picked this right here, and then we're going to define a new field plus, basically, let me call this A, and basically all A is just this, right? So, I mean, I do this just so that I don't have to keep writing square root of m squared divided by 4 lambda. So basically, A is just the vacuum expectation value that I defined right here. It's the magnitude, okay? So what I want to do is I want to shift my 3 field in this way, right? So what this is effectively doing is it's shifting the third field from 0 to this new expectation, okay? So if you do that, what happens? So you take this and you stick it into the potential, and here's what happens with the potential. So your potential, which is a function of phi, becomes 4a squared lambda chi squared plus 4a lambda chi, and then basically b1 squared plus b2 squared plus chi squared and plus lambda b1 squared plus b2 squared plus chi squared all squared minus lambda a to the 4th, like that. So that's what happens to your potential. So what do we have? Well, this term right here, this lambda, if you take a look at this, these are all quartic terms that are basically like 4th power in these fields, okay? You get some overall constant, which unless you deal with gravity, you can always like basically take that constant and shove it away, right? Then you have something new here, which is actually cubic interaction. So remember, the new field, the active field in all this is basically the chi. So it's basically you have 1 power of chi, 2 powers of phi1, 1 power of chi, 2 powers of phi2, and then 3 powers of chi. So basically those are cubic interactions. So that's actually something new. You didn't have any cubic interactions here. And the most important thing is you have a mass term, right? You have a mass term here, which now has the correct sign, right? Here, if you put the minus sign here, you see the original mass we start with is not of the correct sign, but now we have something that is of the correct sign, and good, okay? So, but that's it. Now, I guess I should write down also what happens with the kinetic energy term, and let me do that. So actually, the kinetic energy term is somewhat straightforward, right? Because if you take this and stick it into here, the kinetic energy term is going to be equal to 1/2 mu phi1 d mu phi1, okay, plus 1/2 d mu phi2 d mu phi2. plus, now we do this one goes in here, but notice this is a constant. So basically, since derivatives eat constants, right? What we're gonna get here is 1/2 d mu chi d mu chi, like that. So we have 3 kinetic terms, so 1, 2, 3, and then this is our potential. This is our potential, okay? So and we started with 3 fields, right? We have I equals 1, 2, 3. So what we've done though is looking at the parameters of our theory. So it's the wrong sign. So we look at the new minima, we shift to that new minima, and then we basically rewrite our Lagrange density. And then this is our potential right here. These are all interaction terms. And basically this is a mass term, but notice the only thing that gets a mass term is basically the chi field. The chi field is the only one that gets a mass term. So the other terms, phi1 and phi2, no mass term, they're massless. They are the Goldstone bosons. Okay? So that's so here. Let me write this in red. So they're the Goldstone bosons of the theory. And there are 2 of them. So there's 2 Goldstone bosons. And then there's 1 boson that has like a regular mass. Okay? So again, I'm going to go over the general argument here in a second. And that's probably as far as I'm going to be able to get. But at this point, you can kind of probably get the general idea of how one counts the number of Goldstone bosons in the theory. So basically, we started off with a, I went back to black. Okay. We started off with a group, right, that was SO3 that had 3 dimensions. Okay. We broke it down to a subgroup that was SO2, right, the rotations around the 3rd axis. And this had 1 dimension. So if you take a look at this, then the number of Goldstone bosons is going to be equal to the dimension of this group G, which in our case is 3, minus the dimension of the subgroup H, which is 1. Okay? So then you get 3 minus 1, and that's 2. Okay? So that's how you count the number of Goldstone bosons that are going to occur in your theory. Okay? So let me see if you guys have questions. No? All right. So at this point, I've officially got 5 more minutes, but I have 2 things I could do. So I was going to generalize this argument, right? So that we could arrive at basically sort of a general result here, independent of what specific group I pick. But do you guys feel you already get an idea of how this would play out just based on this, right? Or should I go through the general case?
By general, do you mean like you showed us rotation and then you showed us translation?
No. So what I'm saying, like I would pick a different internal group. I'd pick a different internal group, and then basically show that I would show that basically this. I would show this general formula right here. I mean, I think actually probably, unless you want this is probably okay. Or let me anyway. So what do you guys think? I mean, do you get the idea how you would count the number of Goldstone bosons? So again, you start with some group, you break it down, and then there's some subgroup left over, and then the number of Goldstone bosons is given by this. Okay. All right. Well, if you guys want to see the general, as I do have something written for the general stuff, but actually let me go on. You know, if you guys do want to see it, let me know. So one question is, and this might go back to Tori's question about you know, as you go down to zero, like how are you understanding that that's, you know, as you take the limit when the momentum goes to zero, how is, you know, that giving you Goldstone boson? So I'm going to address that in say the remaining 5 minutes or more. Okay. So one thing you guys will have noticed, or maybe not noticed, is that basically all this is really classical field theory, right? I haven't done any quantum mechanics. Yeah. So maybe quantum mechanics messes all this stuff up, right? Well, it doesn't. So this is an argument that's from Z, and it's deceptively simple. It's deceptively simple. Okay. So I'm going to move on from this and ask the question, like, how does all this play out in quantum mechanics? Because this is all classical field theory. So spontaneous symmetry breaking with quantum mechanics. Okay. So if you have a continuous symmetry, there will be a charge connected with that continuous symmetry. Okay, that's the statement of Noether's theorem. So for example, the phase symmetry of the wave function, right? You have charge. So phase symmetry of the wave function leads to charge. Okay. Now, and that's an abstract internal symmetry, by the way. Now I'm going to jump to other symmetries that you're maybe more familiar with. Rotations in actual physical space. So now I'm talking about actual rotations in actual physical space. They actually also have charges, and those charges are basically the angular momenta. Okay, so the angular momentum is conserved, so that's the charge connected with rotations, and then basically you also have, you know, momenta, which is connected with translational symmetry. You have energy, which is related to time translation symmetry, and so forth. So anyway, anytime you have a continuous symmetry connected with that, there will be a conserved charge. Okay, so I want to write this down because basically I'm gonna just focus on Q, right? But note that basically as I go through this, depending on what kind of group I'm talking about, the Q could have indices on it. So I'm going to write it down as if it were an abelian phase symmetry, just a simple abelian phase symmetry. So it has just a single charge right here. But in the back of your mind, if I realize that if I were doing a non-abelian symmetry, this Q might have indices on it, okay? Just like these charges do right here, okay? So, all right, one way in quantum mechanics to characterize if something is a conserved charge is basically if it commutes with the Hamiltonian. So you have a Hamiltonian that describes your system, and if that thing is conserved with respect to that, then it should commute like that. Okay, so is that something that's familiar with to you guys? You know, if something commutes with the Hamiltonian, then it's conserved. And so this, by the way, means HQ minus QH, like so. So, and again, you could put any one of these things in here, and it plays out. Okay. Now, in quantum mechanics, the way you talk about the ground state is basically it's that state for which you get zero energy. So this is the vacuum, or in simple quantum mechanics, it's the ground state. Right? You might be worried, like, oh, you know, so what if the ground state, like you have a simple harmonic oscillator, so the lowest you can get is like 1/2 h bar omega, right? You can always shift things so that basically you start at zero. Okay, so that you can do like that. So in other words, so if this isn't zero, then what you can do is you can take h and you can shift it by a constant so that this new Hamiltonian is now zero. Okay. Now Now, normally, the vacuum should also be invariant under transformations connected with those charges, right? So for example, right, if I'm talking about this charge right here, if I take the vacuum, then basically this should give me back the vacuum like that. So in other words, the vacuum is invariant under the symmetry connected with that charge, okay? Or what this means is actually Q acting on this is 0. Okay. Well, again, the way you see this is you go, okay, well, expand this, and again, I'm using the abelian type of symmetries as my example, but you know, so if you do the expansion, you've got 1 plus I theta Q plus higher terms, right? But basically Q or any power of Q operating on the vacuum gives you 0. So basically all these higher order terms in here give you nothing. So you just basically have 1 operating on the vacuum, giving you back the vacuum again. Okay. But this is the normal situation. Now we actually have the cases that we've looked at, the symmetry breaking cases. Basically, if you take that Q and operate on the vacuum, in general, you don't get 0. Okay. So if you take so again, these are in some sense like generators of that symmetry. And we've seen, right, that in general, this transformation on that doesn't necessarily give you back the vacuum again, right? In the case of the complex scalar field, there was no rotation in the plane that basically left that arbitrary point that you picked fixed. In the previous case, right, we picked a specific place where the vacuum would lie along the 3 direction. And in general, if we did a rotation in other directions in this internal space, we would go away from that choice. But if we rotated around the 3 axis, we still maintain the same thing. But in general, because those transformations on the symmetry broken vacuum take you to a different location, right? And then so maybe let me put below the vacuum the notation SSB. So this is a vacuum that has symmetry breaking. Now the Q's acting on it in general don't give you back 0. Okay, but right, you can always choose. You can always redefine new states so that do in fact have 0 energy. So how do we do that? So, or we can ask ourselves, well, what are the energy of these states? Okay, so to do that, we want to take the Hamiltonian and operate on Q, operate on this state. Okay, and so I'll tell you where I'm going with this. So this state is it's not the vacuum state. It's not invariant. But now when I calculate the energy, remember the Mexican hat potential. So I'm doing transformations around that ring basically cost you no energy. So they should still be 0 energy. So that's basically what I want to show here. That basically these excitations, right, these things right here, even though they don't take you back to the vacuum, right, they're not invariant, nevertheless are 0 energy. Okay. So let's do this. So what is that? Well, this is actually equal to HQ, that's that, minus QH operating on the vacuum state. Okay. Notice I've inserted 0 here. So basically here it's Q operating on the vacuum first and then H, right? But here it's H first and then Q. But H on this first, remember, you can always shift it to be 0. So this is 0. Okay, so this is legitimate. And then basically what this equals, it equals HQ. It's a commutator of HQ on that. And here's the point, right? This charge still commutes with the Hamiltonian. It's still a conserved charge. It's just hidden. So basically, this is still 0. So it's like, remember, when I wrote down my Lagrangians and I looked at the transformations, the Lagrangians, regardless of how the parameters were chosen, right, we're still invariant under those transformations. We're still invariant under the transformations. but the particular vacuum state was not, right? But basically, this charge still is going to commute with the Hamiltonian, so you still have this. So basically, you have 0 times that. So what you find out is that this is still a 0 energy state. Okay? So these are still 0 energy states. So essentially, all this does is it sort of formalizes that picture of like a marble or ball or a field rolling around the rim of the Mexican hat potential. It costs you 0 energy to do that. That's essentially the formal showing of this, okay? So a couple of comments. Anyway, so basically what you find is that this state, even though it's not invariant, doesn't produce the vacuum back, still is a 0 energy state, right? And basically it's these things that are connected with the Goldstone bosons. And notice in all this is just basic quantum mechanics. Didn't need to use field theory or special relativity, right? So it's really independent of this. And so that's why this is a very broad theorem that applies not only to field theory, right? Quantum field theory or fundamental field theory, but it applies to condensed matter systems and everything. So it's a very, very general theorem, right? And so this is actually the thing that I didn't sort of appreciate before Dan asked the question, is that there's a lot broader context to this Goldstone theorem than just, you know, quantum field theory and fundamental physics. Okay, so I have a little bit more to do. So actually this, and so with this is what Z says is like, okay, this is a proof of Goldstone's theorem, which actually isn't very much. So there are some additional things that I was going to go. Do you guys have like 10 more minutes you want to stay, or you want to try next time, or you had enough, or?
Doug, can I suggest something? I'm going to have to get going because I have another meeting.
Okay.
I think this argument is really interesting because it looks like a proof of Goldstone, but it seems like at no point you had to take the limit as the wave vector of the momentum goes to 0.
That was the next thing that I was going to do.
Right.
That's the next thing I was going to do. So Z has that in the thing. So I'm stealing everything from Z's book at this point. So the first part of this was from Ryder, right?
Mm-hmm.
And then this is basically like Z regurgitated.
Right. So what I was trying to say is this is sort of a crucial point in the whole thing, and I would rather not rush it.
Okay.
I don't know what you think.
No. So okay. So that's I mean that's fine with me. But that's exactly the next thing is like, you know, in the limit when the momentum goes to 0, the wavelength goes to infinity.
Right.
That's the next argument, which is the thing that Tori had asked, right? I think, right? How do you know this is a 0 mass state, right? Right. And
another thing, I don't know if Z has any comments on that, but the original vacuum was defined by Hamiltonian and the vacuum equals 0, right?
Yeah.
Now the Q on 0 state is another state, and it also has 0 energy.
Yeah.
So you could immediately jump to the conclusion that Q on 0 is an alternative vacuum. But I don't remember if Z has an argument against that, because Q on 0 cannot be a vacuum because the guy is not normalizable. The vacuum should be.
Yeah. So he doesn't. Yeah, that's true. But he doesn't mention that. I think he makes some comments like there's some subtleties in this, you know, beyond what I go into or something like that. And then that's about it. So I guess that's one of the subtleties.
Yeah, and actually what I said is not exactly right. So if I take a finite system, so a field theory and a finite volume, then the Q on 0, I think, would be normalizable. But if you take the infinite volume limit, which is the comment that you made last time, in that case, Q on 0 is not normalizable, and so it's not equivalent to the original or an alternative to the original vacuum.
Okay. Yeah, that's a problem.
Right. So it can't be a vacuum, right?
Yeah.
So I guess what I'm trying to say is that the argument is very simple, actually suspiciously simple, right? And you get the hint that there are more things in here that this argument doesn't get to.
Well, you know what? So actually, so Ryder had a version of this argument, right?
Mhm.
That was like way longer, and like when I was working my way through it, I was like, it's kind of clanky, kind of junky. And so this was like really quick, and I was like, I think I understand everything. But again, I think Z probably has swept some of the subtleties under the rug.
I think so. Yeah.
So anyway, but I do have, so the next thing I was going to do. So anyway, I'm ending this with, okay, so this formalizes the sort of marble or field rolling around the brim of the Mexican hat. That's what this is to do. Then the next thing is basically to sort of answer Tori's question, like, okay, if you take the limit when the momentum goes to zero and you construct some of these other states, like, how do you show, right, that the energy goes to zero? So that's what I was going to do next. And then if as the momentum goes to zero, the energy goes to zero, then you have a massless particle or a zero mode. So yeah. So anyway, and then I do have a last bit, which is the Coleman Merman Wagner theorem, which actually is pretty simple. Okay, let me just say again, it's fairly simple if you Z approaches it from the path integral point of view. So if you know the path integral, and if you know some results, like, so there's a standard result for the path integral for, if you take a field phi squared and you take the sort of expectation of it in a path integral way, then it gives you essentially the propagator. And then anyway, so he has a very simple argument for this, but it requires that you know what the path integral is. And so I think you do that in your graduate QM class, right?
Right. So Patrick has seen it, but Dan, I suppose, has not. I'm not really sure.
Yeah, I have not.
Yeah.
Okay. Well, So the thing is so what I'm going to do, I am going to do the Coleman Merman Wagner theorem, but I'm going to just sort of hand wave the path integral. I'll explain conceptually what the path integral is. Then I'll write down the path integral for a phi squared term. And then I'll say, well, if you do standard path integral stuff, the result is this, which then for a massless field gives you a certain type of propagator. And for a massive field gives you a different propagator, right? It's either 1 over k squared or 1 over k squared plus m squared. And the massive one does not have an infrared divergence, so everything's fine. The massless one actually has an infrared divergence if your dimension is 2 or fewer. So basically in 2 or fewer dimensions, things just blow up on you and this whole symmetry breaking picture that breaks down. And that's what I'm going to get to as well next time. And then I have, so if you have stomach for it, then the next thing after that is the Anderson Higgs mechanism, where you introduce gauge symmetries and the symmetry breaking, and you show how basically the curse of massless Goldstone bosons basically cures the curse of massless gauge bosons, because the only massless gauge boson we know is the photon, and we don't know of any, in particle physics, we don't know of any like real Goldstone bosons, right? There are, so I've heard that phonons are supposed to be Goldstone bosons of translational symmetry in the lattice, right? So that, and pions are pseudo Goldstone bosons. They're almost massless, right? And so Z has a discussion of that, but actually, so I'm not going to talk about the pions, but anyway, Goldstone bosons in fundamental particle physics don't really seem to exist because we don't see any massless particles except the photon, and the photon is massless because it's a gauge boson, not because it's a Goldstone boson. So anyway, so let me let you guys go, and then we'll if you guys still want to do the third, maybe fourth series in this lecture, then we'll discuss online. Okay.
Or maybe we can meet in one of the lab rooms.
Yeah. So that's what I'm saying. Well, like this next week, we'll discuss online where to and when to meet.
Oh, yeah, okay.
So maybe 9 o'clock. I mean, the only reason we met at 9 o'clock is because we have that meeting later with Marat. So,
Yeah,
which he moved anyway. So yeah. All right.
okay, good.
All right. Bye, guys.
Thank you.
Bye.